Here we go. Final exam review day. So what I've done is I've put together an outline. Ladies. Of the topics and how many points I would put on it. Okay? But because you're here, as long as we stick to the total of 90 points within reason, I'm a little bit flexible on the distribution of these points. So this is a good jumping off point. But if there's something that you really, really want to show off on, then we can weight that a little bit heavier and within reason. We still have to have, I would say a minimum of 5 points in a category, okay? And so, but if we want to shift some points around, we can do that, okay? But first, give you some time to think about it. And what I want to do is I just want to go through, so for numeration systems, where have we seen that before? We saw it on practice test 1, of course, and then we saw it on test 1. And so I'll just write out, but I need my cheat sheet because I don't have that committed to memory. We saw this on practice test 1, numbers 1 and 2. And we saw it on test 1 as number 1 and 2. Numeration systems, we did change of base stuff. Kind of fun, probably, especially now at this point when you've done it in your other classes. I think probably seen it quite a bit, so that might be fun. But I've got it at 10 points, which is already kind of a lot. Okay. And so, good. How about set theory? That's when we got into chapter 1. So it was on practice test 1, of course, numbers 3 through 9. So you have lots of practice there. Okay. And I know we've already done them. Well, you can revisit them again with fresh eyes. It's been a while, I think, so you can give them a try. We saw it on test 1, numbers 3 through 7 on test 1. Set theory, we did Venn diagrams, right? Which is kind of a fun part of set theory. We also did kind of the union and the intersection, right, of some sets in set theory. Okay. And so, okay, combinatorics. You guys surprised me because you seem to like combinatorics. So I kept it at 10 points. I personally would like it if I was writing the test, which I'm making it, but I don't have to write it. I would want it lower, but we'll see. Kind of keep an eye on that one, right? What's some combinatorics type questions that we could have, right? Oh, you've got cars in a parking lot. How many ways can you arrange them, right? Permutations, combinations, right? All those crazy things which seem like ages ago, right? And so we saw that on, practice test 1 still, of course, numbers 10 through 16. Some are easier than others, right? I like the license plate ones. In fact, I've already written you a license plate one about my personal license plate. It doesn't make it fun, but still a license plate. But I've already written it, so that's 2 marks. So 2 out of 10, already made. On test 1, it was number 8 through 12. So just different things. It included what? It included on your formula sheet the binomial theorem, right? And so I snuck in, this includes the binomial theorem, which we use to expand x plus y to the power of n. So if you don't have a copy of your formula sheet, or if you lost it, might be time to grab a freshie. Okay. If you are missing any of the handouts, please just grab them. I don't want them anymore. Logic. What did we do for logic? We did things like, again, on your formula sheet, if you have an if-then statement, sounds triggering now probably at this point in the term, right? Maybe not when we were introducing logic. If this, then this, right? But now you've probably seen more if statements. And so we worked on the converse, the contrapositive, and the inverse of a conditional statement, right? And so that's part of logic. What else is part of logic? Negating statements, right? De Morgan's laws comes into play, right? That kind of fun stuff. But also truth tables. That was fun. All right, that's solid 4 marks out of 10. Not bad, right? And so, and for judging kind of the weighting of each question, you can look at the test and obviously the practice test, but sometimes I adjust it when I've gone through and actually worked through it. So look at the test, I think, more. But I think I did 4 marks for a truth table, right? Logic. Where did we see logic? It's everywhere. Practice test 1, picking up 17 to 20, and test 1, number 13 to 15. Just kind of broke it up. 13, I want to say, was find the converse, the contrapositive, and the inverse. And then 14 was negate some statements. And then 15 was a truth table, I think. Now, this is where we stray a little bit, and I'm happy to bump that up a little bit. For Boolean algebra, I've only got it at 5 points, as you've already noticed. Boolean algebra was pretty fun. You had to find the DNF and the sum of the min terms. We had 2 different ways of doing it, right? We can expand it by multiplying by a convenient value of 1, right? To find the disjunctive normal form, or you can use a truth table if you want, right? Kind of a, whichever way you want to solve those is fine, but they're usually 5 points, right? 3 to find the DNF and 2 for the sum of the min terms. It's pretty reasonable, which we saw on test 1, still on test 1. Practice test 1, number 21 and 22, and on test 1, it was number 16. 2 for practice, 1 on the test. So this is all from test 1. You've already seen it. You know how it feels in a test situation, right? And so maybe it's been a while, but you can get there, right? Again, just kind of parking lot it, see how you feel about those 5 points. We could just do 2 of them, I guess. But I think 1 is fine. That's why I have it at 5. Exponents and logs. I was pretty unimpressed with the exponents and logs, so I'm gonna keep it at 10. I insist. So no negotiating there. But we're into test 1 now, or practice test 2. Test 2. It was 1 through 5 on practice test 2, and then I only rejigged the format of the question. I made them parts of question 1 instead. That's the only reason. 5 parts. Exponents and logs. Keep an eye out for quadratic equations. Right? You have to solve for x, but once you applied your log laws, you got to an ax squared plus bx plus c, set it equal to 0, you can find those values of x, all right? And so there'll definitely be one of those. I can't remember which part it was on the test. I guess I can find out. D. Part D, or I'll say C part D of question 1 on the test, right? Then what do? We worked with some lines, building up to solving systems of linear equations. And so we saw that on practice test 2, number 6 through 12. And then we saw it on test 2, number 2 and 3, or I should say and or 4, depending on how you solve 4. Because 4 was where I gave you those linear equations and you had to solve the system. I think the easiest thing would be to set them up as a matrix, and so that would lump them into the next section of matrix algebra. But you could have used substitution or elimination. That's totally fine. And so that's how it could be in they're connected, right? And so, we also threw in some absolute value functions in the systems of linear equations, right? Maybe finding the horizontal intercepts of an absolute value function, right? And so we did that on the test. And that was pretty good. So I like to keep some good ones in there too, right? Because this 4th one can be lumped into matrix algebra, I only made it 5 points. We can make it more, but they're kind of mashed up anyways. What's the big deal, right? Got 1 knot, keep it at 5. 1 knot is all it takes. Then we did matrix algebra, right? Knowing when we can add or subtract and scalar multiply and multiply matrices, right? Those rules, finding the inverse of a matrix, right? All those cool things that we did. Practice test 2, it was number 13 through 17, and on test 2, it was number 5. And the and or doesn't really make sense actually, but depending on how you, not or, but and. Maybe I'll do and instead of and or. I don't know. The 4 is kind of floating around. Can be whatever you want it to be. And then relations is the last question on test 2 that we did, right? Things like finding the closure with respect to symmetry. Well, that involves knowing what symmetry means. Well, it involves knowing what the closure is too, the missing relations that would make it symmetric, for example, make it transitive. That's where I said on this test, if you can just look at it, then that's cool. And find the missing links. But on the final exam, I want to see the matrix way. Okay, so I'll make a note of that. I know. What if I can just see it? Yeah. And test 2, number 6. On the final exam, you must, it's all rude in red, you must use matrices to find the transitive closure. Which you did not have to do on test 2. But I will make you do it on the final exam. Mostly because it's an application of all the matrix algebra that we did, right? Multiplying matrices. It is Boolean algebra, and so that's why it's a little bit quicker, I think. Just kind of, if there's a 0, it's a 0, right? If there's a 1 and you're adding them, then it's just 1. Right? And then the only new thing, which I'm also going to force 10 points, just because it's new, we have to test it. And so is functions, which we saw last day. And so this is not tested. Not tested, but it involves things like, what does it mean to be one-to-one? What does it mean to be an onto function? Well, let's take it one step back. What does it mean to be a function, right? We said, okay, all the values in the domain have to be used and mapped to something in the codomain. And the things that are mapped to in the codomain are called the range, right? And what was the other rule? So everything in the domain has to be used up, and anything in the domain can only go to one thing, right? Doesn't have to be a unique thing, but it has to go to one thing only. You can't have a split. And so function definition, I'll move this here. Oops. One-to-one, right, is when everything in the domain maps to a unique element in the codomain, right? Not necessarily all the things, but onto is when all the elements in the codomain are being mapped to, so the codomain is the range, right? And we looked at some examples of the two of them. And given a function, show that it's one-to-one. Show it is one-to-one. I will use the terminology show that it's one-to-one, which means it is one-to-one. You just have to know how to show it, right? Because we need it to be one-to-one for the next part where I get you to find the inverse. Find the inverse. Once you have the inverse, I didn't put it in the list, but here it comes. We use function compositions, right, to prove that it's the inverse. And so prove it is the inverse. And that's it. That's all you need to do. We'll do an example of the functions just because they're the most recent, right? And we didn't really get a chance to do a lot of examples. So it's doable. Basically test 1, test 2, a little bit shorter. Which functions on the end? And I promise they'll be in this order. Unless for some reason spacing is weird on like one page, then I might do a rearrangement. But in general, I just like to keep the same order, right? So that you're not having to also figure out what type of question it is, right? So then you can walk yourself through a journey of the course during the final exam. So I want to do a functions example, showing you kind of what this is. But any questions before we do? No. Yes. Yeah, I draw beans. So yeah, I'd say so. The domain and the codomain, I draw them as beans. You're allowed to draw them as beans. Right. And that might be a nice way to be able to show, okay, what does it mean to be one-to-one and what does it mean to be onto? Right. Would you like a question like that? Draw a domain and a codomain, which is not onto, and explain why. That might be nice. It's kind of fun. Not one-to-one. Or otherwise I could just get you to explain why it's one-to-one. It's kind of boring. Right? You always have to explain why anyways. But it's nice to see the visual. Yeah. Let's do an example. I'll let you think on your questions. You're allowed to have questions. How do I add lines? I'd say the majority of your marks for functions is going to come from this, right? Where I give you a function, you first have to show it's one-to-one, and then you have to find the inverse, and then you have to prove that it's the inverse. Do I risk it? Do I make up a function? Run the risk of there not being an inverse? All right, here we go. We'll see how I do. It might be a total flop. 2x minus 4 over, let's do a hard one, 3x plus 2. That one's hard. All right. Trying to think if there's a rule. Well, I guess we'll know. If it's 1-to-1, we can find the inverse. So let's see if it's 1-to-1. So part A, show that f of x is 1-to-1. How do we do that? A function is 1-to-1 if we're able to show, so here, if f of A is set equal to f of B, then A equals B if f is 1-to-1. So we set the two functions equal to each other, one at f of A and one at f of B, and then we slowly massage this thing until finally we end up at A equals B, hopefully. And that's how we would show that it's 1-to-1. So we've got, we'll start with f of A is equal to f of B. F of x is 2x minus 4 over 3x plus 2. So f of A is 2a minus 4 over 3a plus 2. F of B is the same, but with b's. 2b minus 4 over 3b plus 2. I think we did a linear function last day. And then there were some extra practice ones at the end. Kind of similar to this, stepping it up a notch. How are you going to solve this? I would probably cross multiply these. Right, kind of eliminate the, I'm really, really hoping I picked a decent function. Here we go. 2a minus 4 times 3b plus 2 is 2b minus 4 times 3a plus 2. We can expand both of these sides. I'm going to do them simultaneously because otherwise it's going to take up way too much room. 2a times 3b is 6ab. 2a times 2, my sloppy writing gets me again here, there. Plus 4a minus 12b minus 8. Unless I did some weird math there. Do the same thing on the other side. I get 6ab. Because I'm about to collect like terms, even though I have, technically I'm doing b times a, so you could have ba, but because I want to collect these, I'm going to write them in the same order that I have over here. That's okay. And so 6ab plus 4b minus 12a minus 8. For simplicity, or maybe not, maybe I only think it's simpler, but I usually like to shove everything to one side and set the other side equal to 0. Because then collecting like terms is going to be a little bit easier. Okay? And so what I'm going to do is I'm just going to subtract all these guys over to the left-hand side, or I mean, by the same logic, you can move all these guys over to the right. It doesn't matter. But I end up going like this. So I'm going to rewrite 6ab plus 4a minus 12b minus 8, and then start with minus 6ab minus 4b plus 12a plus 8 is equal to 0. All right. And so here, these starting here have just been moved over. You don't have to write out the step where you're collecting like terms, right? You can just go for it. I am going to, just so you can follow the work, 6ab minus 6ab, right? Just rearranging. Plus 4a plus 12a minus 12b minus 4b minus 8 plus 8 is equal to 0. And you just want to make sure that you have all those. This 6ab minus 6ab is going to go to 0. Negative 8 plus 8 is also going to be 0. So now I'm left with a beautiful 16a minus 16b is equal to 0. Score. Can add 16b to the other side. So then I'm left with 16a is 16b. Divide both sides by 16, even though my b looks like a 6. I get a equals b. Therefore, f of x is 1-to-1. I do want to see this conclusion here, right? I want you to show me, right, that you know what you were going for and why. Yeah. So you do not need to give me, I mean, it's nice, a nice reminder to yourself, maybe what it means to be 1-to-1, but as long as you show me that you start here and then you end here, that's enough knowledge for me. Okay? So you don't need to have the definition memorized. You just need to show me where you're starting, where you're ending, and what your conclusion for that is. Okay, so now we've got a 1-to-1 function, which means that we can find an inverse. Right? So here we go. What did I call it? Part A, probably. B. Find the inverse of f of x. How did we find the inverse? We had kind of two methods. They're the same, right? It's just where you swap your variables. And so how I do it is I set my f of x equal to y, and then I swap my x's and y's, and then I solve for y. And then that's my inverse. So let's start with the original function, 2x minus 4 over 3x plus 2. Let me just confirm. So step 1, set y equal to f of x. You don't have to write out the steps. Those are just to help you because it's relatively new. So y is equal to 2x minus 4 over 3x plus 2. Next step that I do is I swap the x's and y's. Or if you prefer to just solve for x, that's the same thing, right? I'm about to solve for y, so it doesn't matter. Yeah. But you're always going to want to solve for whatever the variable is that's not already solved for, right? And so step 2, switch x and y's, or x's and y's, which means x is 2y minus 4 over 3y plus 2. And then solve for y. I think the easiest way to solve for y here is to cross multiply again, right? And so we've got x times 3y plus 2 is 2y minus 4. Expanding this thing, I get 3xy plus 2x is 2y minus 4. I'm trying to solve for y, which means I want to get all my y's to one side and everything that's not got a y in it on the other side. Right? Or some version of that. Eventually it'll be on the other side. So I'm going to have 3xy minus 2y is negative 4 minus 2x, right? Doing a double move here, where I move the 2y over to the left-hand side, but also the 2x over to the right-hand side. Same move. Why did I do that? Why? To get my y's on the one side, because now I can pull out a common factor of y, and I'm going to do that on the next page here. Y times 3x minus 2 is negative 4 minus 2x. Now I can solve for y by dividing both sides by 3x minus 2. So then y is negative 4 minus 2x divided by 3x minus 2. I'll clean that up. So now, step 4, I guess. Oh, on the next step. Y is f inverse of x. It's kind of confusing that we still use x as the input variable. It doesn't matter, but technically the input of the inverse would be the y's. So it's a little bit backwards, but it's just how we conventionally do it. And so therefore, the inverse function is negative 4 minus 2x over 3x minus 2. That's the inverse of f of x. And maybe I'll just bump this over here. It wouldn't be I'm not ready for this here. Let's see here. I'm just going to bump it over here just for a sec. Because that's the inverse. We're done with that part. What's the next part? Show that the inverse you found is in fact the inverse, right? And so part C, show the inverse you found is in fact the inverse. And then I only brought these down so that we could just look at them. We're claiming that the inverse is -4 minus 2x over 3x minus 2. I will say that there are lots of different ways that you could have solved this, and it's possible that yours doesn't look the same, right? But you could probably rearrange it and make it look like this. I'm not claiming that this is the best way, right? Usually we would have maybe -2x plus 4, right? The negative outside, something fancy like that. But for me, it doesn't really matter how you write it, right? As long as I can follow and see how you solved it. And then if you're able to show me that it's the inverse, then that's cool. That's what I want you to do. So how do we show that it's the inverse? This really is saying show that f of f inverse of x is equal to x, and f inverse of f of x is also equal to x. So apply those function compositions, right? So you need to show me that you can handle these function compositions. And so that's what makes this question so good, is it incorporates all these concepts from this section. And so how do we do the function compositions? First things first, we use the inverse as the input into the function. And if we're able to dissolve it and show that it equals x, that's a good half a step, right? The other half is doing the same thing, because we also know that f composed with g is not the same as g composed with f, right? So we need to show both, right? But we know we're kind of smooth sailing. If we're able to find that the first one is x, then we should be able to pretty easily show that the second one is x. So here we go. I want to have f of, okay, there's a lot of writing here. I'm going to sit down. Sorry. It's a lot of, my table busted. I didn't break it. Yeah.
Show the B again.
Yes. The top or the bottom? Nice. Oh, yes, way better. I'll use big brackets because I have fraction, but I want to use -4 minus 2x. You know what? It's our final exam review. I should probably do it properly. We want to show that f of f inverse of x is equal to x. Now I toss a little question mark up there, right? Just to show that, hey, is this true, right? So eventually that's our goal, is to show that it equals x. It also shows me that you know what you're doing, right? What you're trying to achieve, which is worth something, right? Can't be full marks, but it's worth, part marks if you show me what you're supposed to be doing and finding, right? So even if you hit a snag, because we're about to go down rational function alley here, because what do we have to do? I have to use this as my input wherever I see an x, right? Slow and steady wins the race here. So we need 2. And I encourage you to use nice big brackets, right? Just so you can see the levels. So in place of x, we have to use -4 minus 2x over 3x minus 2. -4 minus 2x over 3x minus 2 minus 4. That's just the numerator. over 3x, but x is, and maybe I don't need to have this much room there. X is going to be replaced by -4 minus 2x over 3x minus 2 minus 2. We need to simplify this until we get to just x, right? Maybe you see it, maybe you don't. I don't expect you to. But what's your first step going to be? You have to, in order to simplify the numerator and simplify the denominator, you're going to need a common denominator here, right? And so how we're going to do that is we're going to multiply 4 by 3x minus 2 over 3x minus 2. That's multiplying by a convenient value of 1, right? We've done that before. And so it forces that common denominator, right? And then we do the same thing down here, right? Because I can't just bring in the minus 2. It's not going to work, right? I need to get this common denominator. So do the same thing times 3x minus 2 over 3x minus 2. I can expand these now. Now that I have a common denominator, I can just put them all over the common denominator. In fact, I can multiply this 2 into the -4 minus 2x if I want to, right? Maybe let's do that first, just so you can see the steps. So 2 times -4 times -2 is -8 minus 4x. That's going to be over 3x minus 2. Minus 4. Should we expand it? 4 times 3? Oops. Minus 12x. Minus 8. Why did this bracket make a difference? You can go -4 times -2, and then you would get to +8, but then you need to replace this with a plus, right? And so I've kept it as a minus and made this minus for now. A dealer's choice. Should end up in the same spot though, over 3x minus 2. All right, so here I'll make a note. We need the common denominator. Just because it's been a while since we worked with fractions, right? And so we need that. Those math skills. Notice when I've got, eventually this will be one fraction, right? And I've got a fraction over a fraction. So then in order to show that, I do an even longer line just to separate the fraction and the fraction, right? So I use different lengths for the lines. So this one's going to be longer. But now we can do the same thing down in the denominator. So 3 times -4 is -12. 3 times -2 is minus 6x over 3x minus 2. Then I'll keep it as minus 2 times 3x, 6x, and 2 times -2 is minus 4 over 3x minus 2. And again, we need this common denominator. Once you have the common denominator to add and subtract fractions, right, then what? -8 minus 4x minus 12x plus 8, expanding in that subtraction and putting it over the common 3x minus 2. Ah, that's looking pretty good. All right, I see a -8 and a +8, but let's not get ahead of ourselves. I do my extra long fraction. In the denominator, I have -12 minus 6x minus 6x plus 8. We'll see. Maybe I did something wrong. Has anyone caught something where I did something wrong? Where? Yes. I'll do it in red because I'm in trouble. Oh, where is it? 4. Is that it? Let's play it out. Maybe it'll dissolve. We'll see. That's what I get for making up a function. -12 minus 6x minus 6x. Oh, here at the very end. Going cross-eyed. There. Right? From here. Oof. It's a relief. Nice. All right. This is again over the common denominator of 3x minus 2. What do you do when you have a fraction over a fraction? Right? You take your fraction in the numerator and your fraction in the denominator, and you flip and then you multiply, right? So this works out to -8 minus 4x. Maybe we'll consolidate. No. Should we consolidate now? -8 plus 8 is going to go away, right? Okay, let's do it. Otherwise, we'll have to write for all night. -8 plus 8, and also -4x minus 12x is going to be -16x. I don't like that. Okay. We'll see. Times. I'm going to flip this fraction. So 3x minus 2 is now in the numerator, and that's going to be divided by -12 plus 4. Something happened. I did something weird. I'll write it out. But what happened? -12 plus 4 is -8 minus 12x. The key here, though, is going to be that these two cancel, right? I'm multiplying fractions, but What's the problem? Hopefully you see what the problem, what my issue is. It's not going to be X. So something happened besides this one that I thought I caught. I'll give you 1 mark on test 2 if you can find it. Decent exercise. I'll try to find it. And the race is on. Hopefully I wrote out my functions correctly. 2x minus 4 over 3x. Oh my gosh. No marks for you. Why? I caught it. Here. 3x plus 2. It's both nice and frustrating to know what the end result should be. You can go back and catch it, but man, that's annoying. Okay, so plus, good thing I didn't distribute it then. And plus 6x minus 4. Yikes, okay. I'm just gonna start fresh here. Hopefully that's the only thing. Looks beautiful. Negative 16x divided by 3x minus 2. Throw brackets on there to show it can be one thing. Times 3x minus 2 divided by, here's the pickle. Negative 12 minus 4 is negative 16. And negative 6x plus 6x, that's going away. And I'm just left with negative 16. But we also said that, okay, the reason we were doing all those fractions is so that when I multiply my fractions, I can cancel those numerators and denominators. And I'm left with negative 16x over negative 16. And to keep it on one page, this is negative. Let's do it again, but with the inverse composed with the function. You have to show both. Man, it'd be really mean if I gave you this rational style function on the final exam. I don't think I would do that. But maybe something in between a linear function and something like this. The problem with this one, right, is that you have x's appearing twice, right? Be easier if you only had x once in there somewhere, right? But then you're just in a y equals mx plus b scenario, right? And so, see, maybe if a coefficient was 1, that might make it easier, right, on the x. But we have to show that the inverse composed with the function is also x. And so just so I don't make the same mistake, and I might actually read it this time. And no guarantees. the inverse composed with the function is equal to x. We do the same thing, just stuffing the function into the inverse. And so the inverse composed with 2x minus 4 over 3x plus 2. Here we go. Keep your wits about you. Negative 4 minus 2 times 2x minus 4 over 3x plus 2. Divided by 3 times 2x minus 4 over 3x plus 2 minus 2. I'm so worried that I'm going to put the wrong thing in. Negative 4 minus 2 times x over 3x minus 2. 2x minus 4 over 3x plus 2. 2x minus 4. Okay. I've passed my initial check. That doesn't really, no guarantees. Should we do it a little bit more swiftly this time? Right? What can you do? Or what I would do is in the same move is I would put the negative 4 over a common denominator and expand this 2 inside. Whether you bring the negative 2 inside or just the 2 and keep the negative outside the brackets, doesn't matter. It's not going to make a difference. So maybe I'll keep it outside the brackets for just a little bit longer. So we have here negative 4 times 3x plus 2. Let's just go for it. Minus 4x plus 8. I know, terribly bold for someone who just mucked it up. New problem. All over 3x plus 2. That's the numerator, right? So now I draw an even longer line separating the two fractions. Right? I didn't show the multiplying by a convenient 1, but I do need it to put it over this common denominator of 3x plus 2. Right? So again, I'm going to expand this 3 inside, but also multiply 2 by 3x plus 2. So I get 6x minus 12 minus 2 times 3x plus 2. Let's not bite off more than we can chew here. Over 3x plus 2. What is class this late? We do, but not for long. And usually students in general are pretty good about picking up when there's no class, but we're not meeting on Friday. This is it. It's game over. So I can be here, but you're off the hook. All right. You can simplify the numerators in each of the fractions, but our main goal, right, getting these common denominators, is when I divide a fraction by a fraction, I can flip and multiply. And so let's do it all in kind of one snazzy step. So I will expand this negative 4 inside. I get negative 12x minus 8 minus 4x plus 8 divided by 3x plus 2 times 3x plus 2 from the denominator of the denominator, 3x plus 2, divided by 6x minus 12 minus 6x minus 4. Okay, looks good. Main event, canceling those 3x plus 2's, right? And then my fractions just merge because I'm multiplying fractions. But I can also simplify some stuff. Negative 8 plus 8. That's nice. 6x minus 6x. And I can collect like terms. And I can get to negative 12 minus 4x is minus 16x divided by negative 12 minus 4, negative 16, which is x. Went a little bit faster this time, right? But we broke it down kind of step by step and working with those fractions in the first one. So therefore, the inverse we found is indeed the inverse of f of x real whopper of a question. Even if you're drawing a blank in the final exam and you don't know how to do it, tell me what you would do. Okay, so tell me that, okay, I would find this function composition and it would simplify until I find x if it's indeed the inverse, right? So tell me what you would do. Show me how much you know, even if you can't do the exact thing in the moment. Okay. Very few of our questions rely on previous parts, which is nice, but also, I guess, kind of annoying. But if you ever find yourself that you're relying on a part that you don't have, just tell me that, hey, I don't know how to find this, but here's a reasonable suggestion. And then just keep going with that. Okay? So I can't really think of any questions like that. It is how I mark, though. Right? If you tell me something wrong in the beginning, right? As long as you follow through with that wrong thing, how are you supposed to know, right? Then you keep a lot of marks. Right? Thinking mostly about the logic section, right? Where you had to write the contrapositive and the inverse and things like that. So, but we're lucky we don't have a lot of questions like that. Okay. Should we revisit the weight distribution? Are you good to lock it in? It feels like a lot of wiggle room, but it's not actually, I guess. Any suggestions? What do you love? What do you want to have a ton of on the final exam? Base conversion. I feel like 10 points is quite a bit. Already. We can do more. Then the juicy question becomes, where are we going to take those marks from? Oh, that's probably more interesting to me. Which ones do you want the least amount of marks for? Although I sense some divide. But we just did it. It's not so bad. Show it's 1-to-1. What's fun about these questions is you always are able to check that you did it right, right? And so, all right, the whole question is, did I do it right? All right. So I mean, I picked this distribution, so I'm pretty happy with it. Double-edged sword.
Less combinatorics, but that might just be.
I'm not surprised by that. I hate combinatorics. Word problems. Ugh. But where are you going to put those marks? Logic?
I could do more Boolean algebra, but I'm also probably the only one.
Boolean algebra is pretty fun. Multiplying by 1 or a truth table, your choice. Some of the midterms. Kind of fun. One single voice. Well, besides the numeration systems.
Matrix algebra, the one where you're taking row 3 times something row 5.
Yeah. So for the matrix algebra, I will make you find the inverse of a 3x3 matrix again. I will make you do, what else can I make you do? You can multiply matrices. Make you multiply matrices. When can you multiply matrices, right? We saw that on test 2. The columns of the first matrix have to match with the number of rows in the second matrix, right? Otherwise we can't do it. And so here, this is going to involve the inverse of a 3x3 matrix. I'll make you do that. But I promise, again, it won't be anything nasty. Like in the practice, what I had done for the practice, it was a disaster. I looked at some matrices. I just grab a textbook. Oh yeah, this one has an inverse. This one has an inverse. That's cool. But getting there, man, it was a slog. Fractions and stuff. So you'll have to find the inverse of a 3x3 and definitely matrix multiplication. And you will have to show me how you found the first entry, right? Show your work for the first entry again, just like on test 2. And so you'll have seen all of those, and you know kind of what they look like. The final exam is not a time for me to introduce any new types of problems, except for, you know, things that haven't been tested. But if it's how you saw it on the test, then, or on the practice, right? Especially I did a great job for test 1, giving you lots of different practice problems and then only testing a few of them, right? Might be worthwhile revisiting those practice problems, right? Because maybe I'll grab from some of those other versions, right? Other types of questions, right? They're still fair game. I just didn't use them for test 1, but I might use them for the final exam. Right? Yeah. What time is it? Oh, nice. Never have that much time. More numeration systems, less combinatorics, more Boolean algebra. Trying to think how I could bump up the Boolean algebra without making you do another one, right? It would just be another version. And honestly, by the time the final exam rolls around, I don't want to do that much marking. either. I know I'm lazy like that. I don't want to mark the same thing twice. That's ridiculous. So, I think I might be tapped out at 5 points for the Boolean algebra. Just one. I'll remove the highlight there. Keep it at 5.
So how would mean you're gonna change?
Well, it was just something I wanted you to think about because they're the ones with less.
I just don't want more systems.
Fair enough. I'll remove the highlight. But I am hearing take a few from combinatorics and put them on numeration systems. That might be nice. Eight and 12. Could go down even more. But some of those combinatorics questions are pretty good too. Right? How many ways can you organize a committee? All right. There. Any other suggestions? Any questions? No. All right. Well, thank you for a wonderful term. Question? Oh, I have a big speech prepared. Yeah, no, I don't.
A couple points off logic and one relations.
Oh, that's juicy. I can get behind that. How many points? Should we start at 2 marks off for logic? Make it 8, but bump this up to 12. I'm into that. Might be nice. I'd be good with 2 more, I guess, but you don't want to put all your eggs in one basket, right? That's risky. Nice. Okay. All right. With that, I release you. You've been good sports. Monday, Friday nights with me. And now we're done. I'll stop the recording, but I'll stick around if you have questions.